Hi, my name is Jameson McGinley, and today I'm going to be discussing assessing transparency of machine self-confidence for autonomous decision-making. So the motivating problem that we're going to be using here is the supervised navigational problem. So consider, if you will, an autonomous system deployed into a hazardous environment as given in the figure on the right. The starting location of the autonomous system is given by this green circle, and the system seeks to navigate this environment to a goal location given by this letter A here. This is a supervised navigation problem. As such, a human operator makes the final decision whether or not the autonomous system should attempt the traverse or not. The question we're really addressing here is, how does the human operator know which decision to make? The human operator overtrusts the autonomous system. They are liable to deploy in situations that actually pose a risk to losing the autonomous system, or if they undertrust it, they may fail to deploy in situations where it's fully capable of successfully navigating an environment like this. As such, they incur an opportunity cost. So our motivation here is to foster appropriate human trust in autonomous systems such that humans can deploy them appropriately. The means by which we do this is factorized machine self-confidence, abbreviated FaMSeC. FaMSeC is a series of interrelated factors that allow an agent to describe its ability to accomplish a task. These factors describe the competency of the agent at each stage of task fulfillment, and the idea here is that these metrics can help influence the human trust in the autonomous system such that they can leverage it more appropriately. FaMSeC is designed for MDP-based problems, that is, problems which have a set of states and a set of actions that you can take in any of those states, such that you can construct a transition model. You incur rewards which you seek to optimize as you solve for a policy to navigate the environment. So those are the kind of problems that FaMSeC is designed for. A chart showing the different FaMSeC metrics is given on the right here. We have our confidence in the interpreted commands from the user to the autonomous system, given as interpreter quality, model quality, assessing the confidence in our model, solver quality, assessing the confidence in the solver, which operates on the model, outcome assessment, which assesses the confidence in our motion plan, past history, which analyzes our confidence relative to previous experiences. For this experimental design, we're going to be focusing on outcome assessment and solver quality. So what is outcome assessment? Outcome assessment is the confidence that a specified margin of success can be achieved based on a set of potential rewards governed by a policy. So if we have a policy, we can do a number of MDP rollouts in which we simulate traces through such a policy. And for each of these simulation traces, we will get a cumulative reward. From n of these traces, we can construct a cumulative reward PDF as shown here in the bottom left, based on all the cumulative rewards that we achieve through those simulations. From here, we have a minimum user expectation. So a cumulative reward that the user expects to achieve at a minimum or surpass, given by R star. On this specific plot, R star is given by this green line, meaning that the user expects at a minimum to achieve 0 cumulative reward through a trait for a run through this environment. R infinity is given as just any one of the cumulative rewards that we get through those simulation traces. And what we can do here is construct this UPM-LPM ratio. So we consider cumulative rewards that achieve at or above our minimum user expectation. We consider the ratio of those to those which achieve lesser than our minimum user expectation. In computing this UPM-LPM metric, we can map this into, we can use a logistic transform to map this into the bounds of -1 to 1, and then finally into a semantic labeling scheme shown at the bottom between very good and very bad, such that we can provide a confidence statement at the end saying our confidence of the autonomous system's confidence in achieving this R star is one of these semantic labels, this R star at a minimum. The next FaMSeC metric that we're looking at is solver quality. Solver quality is to what degree are the approximations used by the solver appropriate for the given task and model. So this FaMSeC metric requires a little bit of narrative. Say, for instance, you really wish that you could derive the policy with which you're operating on using a better solver than you can. Say, for instance, you're trying to derive an optimal policy and you would really like to derive this policy using value iteration. However, you have constraints with your autonomous system and that is simply not possible. As such, you're forced to use an approximate solver in place of such a trusted solver, say MCTS. And what we can do is compare our approximate solver and the cumulative reward PDF that we can generate from that to what we would expect the cumulative reward PDF to look like for the trusted solver. So we can learn a model for what that would look like and make a direct comparison between these PDFs. And we can do that using a similarity metric or distance metric, such as Hellinger distance. And we can take this similarity metric and use a logistic transform to map this between 0 and 2. This is 0 and 2 rather than -1 to 1 as in the previous metric, because there is the opportunity for the approximate solver to outperform the trusted solver in such a circumstance, because the trusted solver is something that we are approximating. We don't actually have access to it. If we did have actual access to it, there is no real reason why we wouldn't be deploying it. As such, there is uncertainty in such an approximation, and there's a potential for the approximate solver to outperform it. So when we take this 0 to 2 bounding and map it into a semantic labeling scheme, values of 1 and above actually correspond to outperforming the trusted solver. This work in FaMSeC is based on our previous CU PhD student, Brett Israelson's work. And Brett ran a user study, an image from that shown on the right. He ran this user study with 255 Amazon M-term subjects. These subjects were given introduction to what FaMSeC is and what it means, and then they had to address this scenario given on the right with the information provided. So essentially, there is an agent here in this road network attempting to reach a goal location whilst not getting caught by an adversarial agent given in red. And subjects, based on outcome assessment solver quality, had to make a decision whether or not they believed that the agent could make it. Subjects were most incentivized to task the vehicle when it was appropriate. However, otherwise, it was in their best interest to decline. And the conclusions of Brett's work were that providing outcome assessment and solver quality had a large positive impact on cumulative score. Providing these metrics had a small positive impact on self-reported trust, and a negligible impact on decision-making time. So the weaknesses with this approach that we're looking to address are, this is a very simplistic problem, of course. It's not very translatable to things that we would see in science exploration or other deployment fields. There is minimalistic user interaction with the agent, such that the human has difficulty actually creating their own understanding of the competency of the agent, and this is a fully observable experimental scenario. So the questions we're left with here are FaMSeC metrics applicable to more complicated problems? Can additional transparency improve operators' self-reported trust in the agent? If we provide justification for where outcome assessment solver quality, will self-reported trust improve? And does the presentation of these metrics change their utility? Hence, what we're doing is looking at a secondary user study with twofold hypotheses. The first being that FaMSeC is more applicable to complicated problems, and second, that transparent reporting functionality allows for improvements in self-reported trust. So we're breaking down this experiment into 4 experimental groups. The first 3 correspond to hypothesis 1, basically taking Brett's work and applying it simply to a more complicated task. And the 4th experimental group adds this transparent reporting functionality to hopefully see an improvement in the self-reported trust in the agent. So here we have a control interface. This serves as a control from Brett's experiment, where a human operator is simply given the scenario and the decision whether or not they should task the agent or not. This is without FaMSeC metrics. And here we have an analog for what the previous work was, where we provide outcome assessment and solver quality, and in a simple fashion, the user makes the decision whether or not to task the agent. For the 3rd control group, we randomize these metrics to hopefully see that the composition of these metrics is useful to the operator rather than simply like a placebo effect as a result of them being present. And finally, we have the 4th interface, where we have added additional elements which justify why the outcome assessment and solver quality are what they are. The user still makes the decision based on these 2 FaMSeC metrics. However, now they have all this additional information with which to see why the confidence is where it is. Ultimately, they still make the decision whether or not the agent should traverse the environment. So to conclude, we discussed investigation into outcome assessment and solver quality metrics from the FaMSeC framework, and we are looking at validating and expanding on results from the existing and previous user study. Our next steps are to actually conduct in-person human trials as opposed to MTurk trials to investigate our hypotheses. Additionally, we are looking to explore the use of the FaMSeC framework outside of MDP-based problems such as reinforcement learning problems. And finally, we're looking at actually how to compute model quality, the third FaMSeC metric, which assesses the autonomous system's confidence in the model that's been given.